All right, so we're talking about area of a circle and portions of a circle. It says here, you can find the area of a circle when you know its radius. Here's the radius over here, okay? And you can use the area of a circle, this is the formula based on the radius, to find the area of part of a circle formed by two radii and the arc the radii form when they intersect with the circle, okay? So if you were to uh, draw a second radius in here, and let me do that here, okay, oops, uh, like that, okay, you have the two radii that they're talking about here, the two radii, and then the arc that the radii form. This is the arc that is formed by those two radii, that portion of the circumference that those two radii carve out. That's portion of the circle has a certain area, and we can use the full area of the circle and say, okay, we can then use that to find out what this is. What we need to know is how much of that circle is, and we can base that on whatever angle is in here. Okay, so let's apply this. See how we do with the application of this basic idea. All right, so finding the area of a circle. What is the area of the circular region, this yellow region, on the wrestling mat? Okay. Remember, we need the radius. Since the diameter is 32, this is showing you the entire diameter from one side to the other. The radius is half of that, or 16 feet, okay, because we want to use from the center to the edge. And we plug that number in. So here we have the area of a circle formula, and we plug in 16 for the radius. And again, remember, you need to just verify, okay, they gave me the diameter, not the radius, so I need to cut it in half. And then when you multiply that, you get 256. And this is the exact area written in terms of pi, right? In terms of pi means you left pi in as part of the formula so that you had an exact answer, okay? But now here we're getting an approximate answer. You can see the wavy equal sign by typing into the calculator, and you'll never be able to write this perfectly because it goes on forever, because pi goes on forever, but we can round it off. So that's approximately what the area is, and even though they didn't ask for it in the answer, if we rounded it off to the nearest square foot, because remember, area is square units, and the units were feet, so we get approximately, or about, 804 square feet. Yep. Okay, so you're going to apply your understanding to this problem, this got it problem. What is the area of a circular wrestling region with a diameter of 42 feet? Okay, you'll calculate that first off by pausing the video and unpause it when you have your answer. There's also this that you should consider before you unpause it. If the radius of a circle is halved, how does that affect the area? How does the area change? Okay, so pause the video now and do those two parts and unpause it when you have your answers. Pause it now. Okay, so we want to use the area of a circle formula. Area equals pi times the radius squared. Now they gave us a diameter of 42. We have a radius then of 21, half of that amount. So we say pi times 21 squared. I happen to know that that's 441, so we get it equal to 441 pi, which if I type into my calculator, 441 times pi, pi is above all of your operations plus minus times divided by, and then there's a little up caret, they call it. Above that button, you'll see in blue the pi button. So you hit your second button and then you hit pi. And when you multiply them, you get approximately, you should get practiced at writing a wavy equals line when you don't have an exact answer, okay? Approximately 1385.44-ish, okay? And we can round that off to then say the area is approximately equal to, if I rounded it to the nearest square foot, I would say it was approximately equal to 1,385 feet squared. Okay? Now, circle that. Okay. And this is going back to a little bit of an earlier lesson, but it says if the radius is halved, how does the area change? Well, we know that if we have a scale factor of 1/2 for a length, which we do, if we turn that scale factor into 2 dimensions for area, we're going to have to square that. So we're going to get half in each direction, or half of a half, which will be equal to 1/4. So we will get 1/4 of the original area. And if you wanted to test this out, I won't do this on camera, but if you wanted to test this out, give a circle a certain radius, calculate its area, and then make another circle with a radius half that, and calculate that area, and verify that it indeed is a quarter of the area of the first one that you got. Okay, that's worth checking. Yeah, that's how you do those. Let's keep going. Okay, so here's the idea of a sector, which is what we need to talk about when we're talking about some portion of the area of the circle. Okay, sector of a circle is a region bounded by an arc of the circle, like here, AB, and the 2 radii to the arc's endpoints. So radius here, OA and OB. Okay, you name a sector using one arc endpoint, the center, and then the other arc endpoint, so A, OB, or in this case, R, P, S. Could you also say S, P, R? Sure. Those are equivalent portions, okay? So the area of a sector is a fractional part of the area of the circle. The area of a sector formed by a 60-degree arc, you basically say 60 is how much out of 360? That simplifies to 1/6. So you're talking about 1/6 of the whole area. So if you wanted to, if this was 60 degrees, which is not, it looks more like 90, but if it was a sixth of the entire circle, you would calculate the whole area and then take a sixth of it, okay? So here's the area of a sector of a circle formula. The area of a sector of a circle is the product of the ratio, whatever the arc measures. By the way, the angle, the central angle and the arc, we both describe those in terms of degrees, the same degrees. So if this was 90 degrees as an angle, this would be an arc of 90 degrees. Okay? So we take the measure of that arc out of a total of 360, that'll give you a fraction of the circle, and then you multiply that by what the total area is. So here they write it. If you wanted to know what the area of this shaded portion of sector AOB was, you would take the measure of arc AB, which is the same as the central angle's arc, or measure, divided by 360 to get a fractional amount, and then you multiply that by whatever the area of the circle is, as used in the formula pi r squared. Okay, so that's what we're going to do. It's a pretty straightforward concept. We're going to apply it now, so let's check it out. All right, so we want to find the area of the sector here, okay? What is the area of sector GPH right here? Leave your answer in terms of pi. That means we're not going to multiply it by whatever the calculator gives us as pi and round it. We're just going to keep it in terms of pi. So we say, what is the measure of GH? We divide that by 360, and then we multiply it by pi r squared. Now, just to point out here, what fraction of a circle's area is formed by a 72-degree arc? Okay, so the area of a sector formed by a 72-degree arc is 72 over 360, right? That's what we're just doing. We're saying that amount of degrees divided by 360, and that's 1/5. So we're going to take 1/5 of the entire area. Yeah? Okay. So what do? We plug that in here. We see that 1/5 of this is 45 pi. And just for fun, watch, if you wrote that out, if I wrote over here, I'm going to rewrite it so that 72 over 360 is just 1/5. And we say 1/5 times 15 times 15, because it's 15 squared, times pi. You can see that 15 is really like 15 over 1. And if we canceled top and bottom, we could divide these both by 5. We would get a 1 down here then and a 3 up here. And that right here, this 3 times this 15 is where you get the 45 from. Okay, so you can write that out yourself if you wanted to, but you have a calculator, you can use that as well. Anyway, that's it. So the area of sector GPH is 45 pi, and don't forget the units, squared. Whatever the unit of length is, we use that squared for the units for the area. Okay, now it's your turn. Circle has a radius of 4 inches. What is the area of a sector bounded by a 45-degree minor arc? Leave your answer in terms of pi. You're going to pause the video now. You're going to calculate this out, and when you come back, you will check your answer against my answer. So pause the video now. Okay, so the way that we're going to calculate this is we're going to say the measure of, or let's just say 45 degrees. We don't have the names for it, so we'll just call it, say 45 degrees out of a total of 360 times pi times the radius squared. Okay, and actually I can put in the radius. They gave it to us as 4, so I'm just going to put in a 4 squared there. Okay, and what is 45 out of 360? Well, you can do the math to figure out that it is 1/8 of 360, which makes sense because 90 degrees is a fourth, but you only have half of that. So you have half of a fourth, and 1/2 times 1/4 is 1/8, times 16 pi. And of course, if you were to cancel this 16 on the top, I say on the top because it's over 1, and this 8 on the bottom, we get a 1 here and a 2 here. And then we get as an answer, we have 2 pi inches squared. Yep. We leave our answers in terms of pi because that's what they asked us to do. That's it. Good. Hopefully that was pretty clear and made sense. Let's keep on going and see if they can challenge us a little more, because I think so far what we're doing is pretty straightforward, and you're like, what's the hard part of this? And so far, maybe it hasn't come yet. So let's see what else they got. Okay, so this is where it might start to get a little bit, not harder, I mean, I think you can do it, but just a little bit more of a challenge. So, watch what they say here. Part of a circle bounded by an arc and a segment joining its endpoints is a segment of a circle. So right here, okay, you've got, let's look down here at the key concept. You've got 2 radii, right, and this arc. And so this forms some sector. Now, if you took those endpoints right there and you connected them, right, you would then say, okay, there's some area of this triangle right here that we could figure out. We actually have been introduced to a formula for that, which we'll get to in a second. But if you took all of that and then you took away this triangle part, what you'd be left with is this segment of that circle that's left when you remove the triangle part of that sector, okay? That's the big idea. So to find the area of a segment for a minor arc, draw radii to form a sector, and then the area of the segment equals the area of this whole sector minus the area of the triangle that's formed when you connect those endpoints, like I just said. Cool, okay. Let's do one and see if this presents a challenge to us. Okay, now this is the last problem, however, and I know that it looks complicated, and in fact, it is a bit complicated. I read this problem and I thought, well, why are you doing it this way? And I'm going to propose what I think to be an easier, better way for you to think about it and do it. I'll do that on the next slide, but the first thing that I want to do is I want to just talk through what they did, because you should understand what they did here, okay? Let's talk through it. And we'll deal with the got it problem. Maybe you can choose to do the got it problem the way that I'm showing you. Okay, so let's talk about it first. So what is the area of the shaded segment? Okay, this segment over here. Round your answer to the nearest tenth. So what they say, what do we know? We know the radius, and we know arc AB is measuring 60 degrees. We know that CA and CB are congruent and equal in measure, and we know that the measure of ACB, right, which is the same as the arc measure of 60 degrees. Now, what do we need to know? Well, we need to find the whole area of the sector, and then we need to subtract away from it the area of the triangle ACB. So that's the plan. Subtract the area of triangle ABC from that whole area of the sector. Should be understandable of what we're doing there. Now, first thing we need to do is we need to find the area of the sector. My method, you're going to have to do the same. We're going to say, what's the measure of arc AB? It is 60. That's 1/6. Okay? And what is the radius? It's 18. So if you did pi times 18 times 18 times 1/6, we get this. We're going to keep that. I'm going to circle this. This is a valuable piece of information here that we're going to need. Yeah? Now, this is where I diverge from them. I'm doing mine differently, but this is what they do. They say triangle ACB is equilateral, okay? So we know that this is 60 degrees, and therefore dropping an altitude down, because if we want to do 1/2 base times height, we would say, okay, we drop that altitude, we split that 60 degree angle up here into 30 degree, and we get a 30, 60, 90 triangle there, okay? So if this is 9, then this is 9√3, yeah? Okay, and that's cool. Now the area of a triangle is 1/2 base times height. The actual base is that full length of 18, and times the height, which is 9√3, take half of that, right? And you calculate that to be 81√3. That's how you can do that, okay? But what if it was some other weird angle there that wasn't so easy? You could use trigonometry to find that side length. I'm going to propose a different way. Okay, but anyway, let's say you found the area of that triangle. You can say the area of the shaded segment is the area of sector ACB, which we found up here, minus the area of this, which we found down here. And when you do that in your calculator, you get this amount, okay? So the shaded area, the area of the shaded segment is about that much. Take note of that, okay? I'm going to copy this onto the next screen, and I'm going to propose another way before you do your got it problem. You can choose to do it whichever way you like, but let me do that first and see what you think about my method. Okay, so I realized why they're not doing it my way, and I'll show you my way, and then you'll have to understand when you can use my method and when you can't. Okay. So here we go. This is the big idea here, is this theorem right here, okay? If you know the length of two sides and an included angle, and if you look up here, that's what we have, right? We have the length of two sides of a triangle and the included angle here, okay? Then you can use this formula, 1/2 BC sine A. Now, the trick with this is this works for only acute angles. This is an acute angle, and so that's fine. If you understand what happens for sine when it goes above 90 degrees, what happens is that for every degree above 90, it has the same sign as it does below 90. So like the sine of 95 has the same as the sine of 85, right? 5 degrees before 90, 5 degrees after. They have the same. So if you did it for an obtuse angle, you wouldn't actually find it. Okay, so this would only work if it's an acute angle, but you can use 1/2 BC sine A. So I'm going to do that for here, and I left here, right here on the bottom, the answer that they got. Oops, right here, and watch what we do when we calculate this out using this particular formula. Okay, we say 1/2 B, which is 18, the radius of the triangle, times C, the length of the other side that we know, which is also 18, since it's the radius, it's the same, times the sine of 60. Okay, and if we type that into our calculator, we type in 1/2 times 18 times 18 times sine of 60, we get approximately 140.296, or let's say 0.3 approximately, right? Now, if you typed into your calculator, what is 81 times the square root of 3, which is what they have right here, you get the same number, approximately 140.3. So if that seems easier to you, oops, Sorry about that. If that seems easier to you, you can do that, but you can only do that provided you have an angle less than 90 here. Okay, but if you do, then it works. And of course, when you plug in those numbers, you're still going to get the same answer. So again, you can use this theorem, and it's not noted in this theorem here, but it was noted in the notes before when it was introducing it. It has to be an acute angle. Okay, if you want to use that, you can. Let's go to the got it problem and do it, and then we'll be done. Okay, so well, actually, and you know what, when I said it has to be less than 90, it could also be 90. That would also work as well. But what is the area of the shaded segment shown at the right? So let's do it their way, okay? Just so that we know how to do it regardless of whether it's acute or an obtuse angle or a 90-degree angle, okay? You're going to do it. You're going to calculate it out. You can do it this way. You can think of this triangle. I'm just going to give you a little bit of a booster here. You can think of the triangle that they're making here like this. It is a right triangle with a 4-meter length of side there, okay? And since that's 90, what would happen if you dropped this altitude down right here, okay? Try and figure that out. If you know what's going on here, what kind of triangle you form, you'll be able to solve this, okay? So pause the video, see if you can do this. If you can't, you can use my method, and because this is not above 90 degrees. So pause the video now and give an attempt at trying to find the area of that yellow segment by finding the area of the sector minus the area of the triangle. Pause it now. Okay, so what are we looking at here? We are looking at this triangle here, right here, being, since this was 90, we're going to split that in half to 45, and what we get then is a 45, 45, 90 triangle. This is 45, so that, and that's the 90 degrees there. Okay, so what? If we know that this is 4 meters, then what do the legs look like for the 45, 45, 90 triangle? Well, remember, it's always this amount right here, x root 2. I'm sorry, if this is x, then this is equal to x root 2, right? The hypotenuse is x root 2 when we have a 45, 45, 90. So what we're basically saying then is that 4 is equal to x root 2, and how do we solve for x? We divide both sides by root 2. So we get 4 divided by root 2 is equal to that length right here, x, okay? That right there. That means then the whole base of that triangle all the way across is going to be twice that amount, or 8 divided by root 2, okay? So I'm actually going to take a screen grab of this, kind of drag it over here and blow it up and rotate it so we can just see what we're looking at, okay? This is 4. That means, again, if we drop this altitude down right here, if this is 4, then this is 4 divided by root 2, and I'll draw that altitude so you see it. And as I said, then each leg is 4 divided by the square root of 2. So this equals 4 divided by root 2. That's going to be the altitude, or the height of the triangle. And since it's a 45, 45, 90, this portion right here is the same amount, 4 divided by root 2. So since the whole thing is twice that much, that is equal to 8. This whole base right here is 8, double that amount, right? 8 divided by root 2. Okay? So we can find the area of the triangle by saying 1/2 the base times the height, so 1/2 this base times this height, and I'm going to write it over here and calculate it out, and then we'll have it and we'll save it, okay? 1/2 the area of the triangle, triangle, we call that RQP, right? RQP is equal to 1/2 the base right here, 8 divided by root 2, times the height right here, right here, 4 divided by root 2, okay? And we'll find the area if we multiply all this together. Well, fun fact here, watch. Root 2 times root 2 is just 2. Anytime you multiply something in the root by the same amount, you get what's inside without the radical on it. So root 2 times root 2 is 2, times this 2 is 4, so we got a 4 in the denominator, over 1 times 8 is 8, 8 times 4 is 32. And of course 32 divided by 4 is exactly 8. So we have an area for that triangle of exactly 8 square meters. Okay, sorry about that M. It's a little funny when I'm down at the bottom of the page. I get menus pulling up when I try and write. Okay, but let me do a little bit better. Actually, I can just do a little bit better. That's an M. Yeah, 8 meters squared. So that is what the area of the triangle is. Now we need to go back and find the area of the entire sector. So I'm going to erase all of this junk. Yep. Thanks for your patience while I erase this. We now need to use the formula for area of a circle, which is pi r squared, and we need to find out what portion of the entire area we're dealing with. So we say, okay, for the area of that segment, or that sector of the triangle, we say 90 out of 360, or it's going to simplify to 1/4, right? Times pi times the radius squared, okay, or 1/4 of 16 pi, and 1/4 of 16 pi is 4 pi. So we have the entire sector being equal to 4 pi, and then we subtract away the area of the triangle, which is 8 meters squared. Okay, so if we did that, we would say 4 pi is the area of the sector minus 8. And you can't do 4 minus 8. You have to do 4 times pi minus 8. Okay, and if we type into our calculator 4 times pi minus 8, we get approximately 4.566. It says round to the nearest 10, so that's approximately 4.6. And what's the units? The units are meters, so meters squared because we're talking about the area. That is the answer, 4.6 meters squared. I'm going to circle it and mark it, but then I'm going to do it my other way as well, okay? Just really quickly. We already know that the area of the triangle was 8 meters squared. If we typed it in to our calculator, just to check and see that we get the same area by using my formula, remember it works for up to 90 degrees, but not beyond it. What I'm just going to do real quick is just say, what if I wanted to find the area of the circle, or of the triangle right here, 8 meters squared, by doing our formula. We know that the area of a triangle can be calculated by using 1/2 BC times the sine of the angle A, okay? And if we type in 1/2 of B, 4, times B, 4, times the sine of A, which is the sine of 90, you might not know this off the top of your head, but the sine of 90 is actually 1, and you can check that by typing it into your calculator. Okay, so you get essentially 1/2 times 4 times 4 times 1, or 1/2 of 4 is 2, 2 times 4 is 8, 8 times 1 is 1, so you still get 8 meters squared for the area if you do that method. Again, one more time, this formula only works for up to 90 degrees and not beyond it. So if you see it going beyond 90 degrees, you're not going to be able to use that, and you'll have to just drop an altitude and use trigonometry to find the base and the height. And that will matter what the central angle is. The altitude will split this in half, and you will use that to be able to find that, and this with trig, and you'll double it for the base. Yep, that seemed like a lot. Maybe that was the complicated part that I was alluding to earlier. Anyway, that's how you do it. Good luck.